Hello, so today we're going to be talking about the real bare minimum or the basics of atomic structure, of what it is known today, and what I expect you to know of atomic structure within this unit. So the first thing is we kind of just dive into atoms. We've already talked about this plenty of time before, but we're just going to review a little bit. It is the simplest particle of an element, or how to identify the element. It contains all the chemical and physical properties of its representative element. So calcium atom represents the physical and chemical properties of calcium on the periodic table. It's composed of two parts, a nucleus and a large cloud of electrons. The nucleus is the central core of the atom. It represents 99% of the mass of an atom. So a huge majority of the mass of the atom is located in the nucleus itself. And that nucleus is composed of protons and neutrons. Now, protons, they are positively charged particles found within the nucleus. They're used to identify the atom and the element on the periodic table. So there's such a thing called the atomic number that we'll talk about later on that identifies the atom and element itself. The number of protons is the same for any atom of the same representative element. So, for example, a hydrogen atom is always going to have one proton. If it has two protons, that means it's a helium atom. So that's how we distinguish the subatomic nature of each individual element. Typically, protons are notated by P+, P meaning proton, and so little p, lowercase p, with a positive charge, just a relative positive charge, saying that that particle is positively charged. Electrons are negatively charged particles found outside of the nucleus in a large cloud. Have incredibly small mass, and depending on the application that you're using, the mass can be considered negligible, which means it could be considered weightless. But it is very dependent on what you are talking about, what experiments you're doing, and everything like that. So if we do consider the mass to be negligible, I will clarify that later on in the semester and throughout the school year. Typically, electrons, you'll see a lot of me doing this too, since electrons can kind of go from place to place, is a little lowercase e with a negative as a superscript. So again, it's just E representing electron, negative meaning a negative charge. Neutrons are neutrally charged particles found in the nucleus of the atom. Neutrally meaning that it has no positive or negative, it's canceled, so it's just has no charge whatsoever. The number of neutrons may vary among atoms of different elements and of the same type of element. These difference in neutrons is what develops what's called isotopes, which again we will dive further into in this unit. But isotope is something that has the same number of protons but a different number of neutrons. So neutrons can change without changing the actual element itself. But if the protons change, then the element itself will change. Typically, you can see neutrons being denoted as a little lowercase n with a 0 in the superscript, meaning zero charge. Okay, so atomic number. Atomic number is the number of protons in the nucleus of a particular atom. So the atomic number is what's used to organize the elements in the periodic table in ascending order. It's used because the number of protons of that particular element cannot change again. I mean, if you change the number of protons, it means you change the element itself. If a proton is removed or added, it becomes a new element. The atomic number is always going to be the top number. Now, in some periodic tables, you may see the number in the top left corner, the top right corner, or the top middle. But either way, that top number is the atomic number itself. So if you look at a hydrogen block, it'll have 1. That means it has an atomic number of 1, which means it has 1 proton within its nucleus. In this case, silicon has an atomic number of 14, which means it has 14 protons within its nucleus. The mass number. The mass number is the addition of the number of protons and the number of neutrons within the nucleus. Okay, now mathematically you can distinguish it as this. Protons plus neutrons equals the mass number. The notation that we just kind of described for each subatomic particle, you can also notate it as this: P++ N0 equals M hashtag. I use it as M number. It's, you know, whatever way works best for you to memorize this formula. It does not matter, just whatever works best for you. It's just if you want to use the notation that I described earlier, that would be the more appropriate way of doing that. Another way you can kind of describe it too, since the number of protons is equivalent to the atomic number, you can also say it's the atomic number plus the number of neutrons within the nucleus equals the mass number. Okay, so some problems I may say there is a nucleus with 17 protons, or I could tell you that silicon has 17 neutrons in its nucleus. What's its mass number? That means you have to go to the periodic table, see the atomic number for silicon, and determine what the mass number is. The mass number is denoted in what's called isotopic notation, which again we'll dive a little bit further into when we further discuss isotopes. So isotopic notation is when you have an element symbol, but it has two numbers. There's a top number and there's a bottom number. And so the top number is the mass number. So it's the addition of protons and neutrons. So what this is saying is that there are 14 protons and neutrons collectively within the nucleus. But the bottom number is the actual atomic number. So the thing is that since we know that the atomic number, wherever my cursor is, since the atomic number is 7, we can say that there's 7 protons within the nucleus. Well, if there's 14 protons and neutrons collectively together, we can say 14 minus 7, there are 7 neutrons within the nucleus. So there are 7 protons, 7 neutrons, collectively adding up to 14, which is the mass number. So again, kind of break this down, you would manipulate the equation to solve for the number of neutrons, mass number minus the atomic number, and you can say 14 minus 7 equals 7. So average atomic mass is the average mass of all known isotopes of an element. Again, we'll dive further in isotopes, but it's important to identify the numbers that are on the element block of each element on the periodic table. It's expressed in atomic mass units, AMUs, not grams. Okay, so atomic mass is defined in AMUs, not grams. We will convert those later on into later units, later chapters and units within the class. But for right now, atomic mass is described in atomic mass units. The unit of AMU is derived from the mass of a carbon atom. We know that carbons have 6 protons and 6 neutrons. Well, an AMU is 1/12 the mass of a carbon atom. Now, since protons and neutrons are 99% the mass of a carbon atom, because the electrons really have negligible mass for the most part, we can approximately say that an AMU is approximately the same mass as 1 proton or neutron, considering that the mass of the electron does not matter. Okay, now that is an assumption. That's not true, but for pretty much 95% of the stuff that you do in my class, you can assume that's okay. Okay, but as you go further along into your academic career in the sciences and everything, the mass of electrons will become more prominent, and you will have to start letting go of this assumption. But for the basics of chemistry, you can assume this. So again, the atomic mass, we already know the atomic number is the top number. We know the chemical symbol is in the middle. So the average atomic mass is actually the bottom number. You can always think that the average atomic mass on an element block is the one that has a decimal place. Okay? Every single element on 99% of all the periodic tables are going to have a number at the very bottom of the block that has decimal places to it. Okay? That is the average atomic mass. All right, so this was kind of a short video, which is kind of okay, but it's kind of really the basics and maybe a review for atomic structure that you've already experienced in other classes. So feel free to talk to me if you have any other questions. Otherwise, in the next couple of videos, we'll start diving deeper into those concepts, how to apply certain calculations, how they're useful in regards to conceptual ideals of chemistry, and so on and so forth. So thanks for joining me on this video, and I hope to see you soon in the next, and see you in class. Bye.